chapter, in the last chapter, we have discussed that what are minterms, what are maxterms, and I also give you idea about why do we need this minterms and maxterm. Actually, the Boolean functions which we have, we need to simplify it. And why do we need to simplify it? So that our circuit can be implemented with a minimum number of gates. If gates will be minimum, definitely the size required to build a circuit on a PCB, printed circuit board, will be less. If less number of gates will be there, the speed of the operation will be high. Other thing, third advantage could be like, if less number of gates, so the price will also be less, okay, of the circuit. So because of these advantages, we have to simplify our Boolean expression. So we have learned one of the example in previous chapter. How can we simplify this one? So the process to simplify the given Boolean expression using Boolean's laws. So we apply some Boolean laws and we can simplify the given Boolean expressions, as we have also solved some of the questions, like 3 or 4 literals are given and we reduce to 2 literals or 1 literals, like that. So this is the advantage basically, okay. And the other thing what we are going to learn now, the another method by which we will be trying to simplify the Boolean expression, that is called map method. So map method, if we want to use the map method, so the advantage of the map method is that the function which you will receive after simplification from the map method, that will be the reduced one. Further, we cannot reduce it. So maximum reduction is possible using map method, because sometime while we are applying basic rules, postulates to simplify, we are not sure whether we have reduce the maximum or is there any chances for the to reduce maximum. But here the solution which you will be getting, that will be the maximum reduction. Sometime you may have more than one solution of simplification, but both of them will be satisfying the minimization criteria. Most of the time 95% solution will be single solution, but sometime possible we can have multiple solution, but both will be implemented using the same number of gates. So we'll see this one by one. So let's start with the what is this K-map method. So this method is basically, girls, this is the chapter 9 we are going to cover. This method. So in map method, girls, we used to have a square inside the map. Each square is correspond to a minterm. Hope you understand the minterm. Minterm is basically a product term which consists of all the literals of a function. Okay. So even in other words, we can say a minterm is basically canonical form. Yani we have discussed canonical sum of products. Sum of products. Sum of products, the form is look like that. Okay, just let me write for you. Maybe it will be a quick review for you. So sum of it is like f is equal to a b. Okay, I'm writing a b c complement plus a b c. It could be a complement b complement c, like that. Okay, so this is what we call this one.
Canonical.
Yeah, canonical. Yeah, everyone knows this one. This is called canonical sum. Now, this canonical sum could also be called as, what is that? I can also say sum of minterms, because the one which is given to us, these are the minterms. Like 1 is correspond to 1, b is correspond to 1, c is 0. Plus, what is next? A, B, C, yani 1, 1, 1 plus 0, 0, 0, 1, right? Which could also be written as small m6, the first one, plus m7 plus m1. So these are what? These are minterms. And so I can also say sum of minterms, okay, or canonical sum. So if you want to use the K-map method, I must know all the minterms. If I know, then I can use it. Otherwise, not. So if Boolean expression is given to you, which is not in a soft form, not soft, maybe in soft, but it is not canonical, any standard. So if something is standard, we cannot find the minterms. So we need to convert it into canonical first, so that we can know the minterms. Once I know the minterms, I can simply say, okay, these minterms are minterms. I have 1, 6, and 7. Then I can use the K-map and simplify that one. All right. So, okay. So let me just go to. So let's start with the examples. Just remove this one. Next, this is two variable K-map. Two variable K-map, yani two variables means if we have variable X and Y, so we can simply use this one. Okay, this is K, two variable K-map. No, so two variable is not much important because it's just for idea. Usually three variable or four variables comes in So let's say it's good to know two variables has four midterms. Why four midterms? Because with the help of two variables we can generate four different combinations, right? So four different combinations would be like that: x complement y complement, x complement y, xy complement plus xy. These are basically M0, M1, M2, M3 minterms. So in K-map, each square is basically correspond to one minterm. So because if we have two variable, so we can have maximum four minterms. So there are four places for each minterm. Okay. So how do we recognize a place? We write here x and y, x the row wise and this is column wise. Then we can find the address of it. Like you will be reading xy. So if you read for this first square, what is the value of xy? You will say 0, 0 because x is 0 here, x is 1 here for this row. And because this is a single variable y, it could have 0 value or it could have 1 value. So if I read for this square, so I will say 0, 0. 0, 0 means x complement, y complement. So this place is reserved for M0 entry. Next one, 0, 1, any x complement y. So M1 is, this one is reserved for M1. This is for M2, this one is for M3. So if I have given a question, a function, for example, which is having only single minterms, let's say if we have a minterm, what is that? X and y, bus function, this one. Okay, so how I will be placing the entry? Because this is minterm. What minterm is this? M3. So M3 places this one. So it will be placed here simply. Now let's say if I have function differently. Okay, what is that? Let's say if I function this, and I'm having terms M1. If I enter M1 comma or plus whatever M2 plus M3, so three terms are there. So if I have three terms, simple. So their entries will be, because M0 is missing, so these will be placed like that, 1, 1, 1, 1, like that. So that will be missing here. Okay, that will be missed here. All right.
Okay.
So let's, because I just mentioned variable is not very much important, so we have to move to the next one. So next, yani three variable. I will start with the three variable. That will be easy to understand. So three variable move. So their combinations will be 8. You know that. So three variables can produce 8 map. So yani I will be having 8 squares. You can see like that, 8 squares. All right. So 8 square now. So x, y, z. Let's say we have x, y, z three variables. So we are placing here x here and yz here. So x, because single variable, so we will be having its value either 0 or 1. So we are having two rows. Now yz is basically two variables. They can produce 4 different combinations, which will be like 0, 0, 0, 1, 1, 1, 1, 0. You may think why I am writing here 1, 1 first. Why not in an order 0, 1, 2, 3? But this is 1, 1. Actually, this numbering is not in binary. This numbering is in gray code. So it is like that: 0, 0 will be first column, 0, 1 will be second column, 1, 0, yani 2 in decimal will be the last one, and 1, 1 is in 3 basically. But it is a gray code as I mentioned. So it will be 0, 0, 0, 1, 1, 1, 1, 0. This is the fixed rule. We cannot change it. Now later on we can check the address of each minterm, like x's value is 0 to this one, y0, z0. So this will be M0 entry. You can see here M0, reserved for M0. Then M1, then it will be 0, 1, 1. It's gonna be M3. So actually all the time I'm not going to read x and z values. There is a, you know, the very easy way to know this is how to find the minimum minterms positions: m0, m1, m2, m3, m4, m5, m6, m7. Khalas. Now we will see our given function. What are the minterms there? But simply, if there is a minterm present, we will place 1 to that particular minterm, else we will leave the remaining. So let's see now. We have given a function. I will do one thing, guys. I'll take, I will use my mobile phone and open the whiteboard for you. That will be more easy, inshallah. Okay, just give me 1 minute. Stop sharing from here. And from here, I will share the whiteboard. Okay, all right. Can you see the whiteboard, girls?
Yes. Yes.
Yeah, white blank screen, right?
Mm.
Okay, so now I am assuming a function. I am assuming a function. I have given f, just a minute, the right color. All right, I have given f is equal to all right. So I have given f is equal to x. What happened? X, y, complement and z. Let's say I have given this one x, y, z. Okay, and I have to simplify this one using K-map. Okay, let's see first. We try to solve it first by using basic laws. Then I will be solving by the K-map and try to match whether we are getting the same solution or not. If I want to apply here basic rules, so I will see what is common to both the functions. So I will find that xz is the common, and inside I will be getting y complement y. And do you know y complement y is what?
1.
Y complement, yeah, 1. 1 multiplied by xz will give me xz. So this is my reduced function. Let's try to simplify this with the help of K-map. So when I see this one, I'll try to know first what are the minterms, girls. So when you see this one, x is 1, y is 0, z is 1. So it is what basically 1, 0, 1. This is 1, 1, 1. Yani I have two minterms which are 5 and 7. Clear? Is it clear?
Yes.
So two minterms are given to me. Now, because the maximum number is 7 here, so I know that, and 3 variables are there. So I have to have 8 squares, yani 3 variable map solution. So I am drawing the map here like that. Okay, this is the way, like that, like that, like that. And here I will be writing x, y, z. And this will be 0, 0 as I mentioned, 0, 1, 1, 1, 1, 0, 0, 1. All right. Now just place the entries. Okay, so entries, yani two minterms. As I mentioned, this is 0, 1, 2, 3, 4, 5, 6, 7. I'm writing small so that you can just got the idea where to place these minterms entries. Now you see 5 and 7. So this is 5, just place 1 to this minterm, and this is 7, place to this one. Once we place the ones, this is placing. Now second thing is that we have to make the group of ones now. Group of ones, we have to combine these group of ones, we have to make a pair of it. Here are some rules which we should know. The very first rule is that you need to make the group the largest group always. Largest means the group you will be making with that should be in a power of 2, like that. Power of 2 always. You cannot make any number of ones in a group. You cannot combine them. So if you go for the power of 2s, 2, 0, it will be 1, then 2, 4, 8, 16. So you are getting idea from here. You can make a group of 16 ones, 8 ones, 4 ones, 2 ones, and 1. You cannot make any group of 3 ones, group of 5 ones, 7 ones, 6 ones, not allowed at all. always the grouping which you will be making, it should be a power of 2, which I just mentioned. It should be 1, 2, 4, 16, 32, whatever, and so on. It cannot be any other. First rule. Second rule is that always you will try to have a larger group. And you will not say group 1, group of 1, group of 2. No, always look first what could be the maximum group that can combine maximum number of ones. So this is our prime aim, to have larger group. All right. Now, if you see the entries, how many ones are there? Only 2, right? So maximum group, what it could be? Can we make a group of 4? No, because two ones are there only. So my group will be having maximum 2 ones. Am I right?
Yes.
Okay. So just I have to combine them. Okay. So my group will be like that. I will combine them this way. Make the group. Okay. And hope you should always remember in your one thing. Why we are using this K-map? We are using K-map to reduce the function. Larger the group, lesser the min term in the solution, lesser the literals in the solution. Okay, so that's why the aim is to have larger. So here we make it. Okay, after combining them, you have make sure you have combined all the ones in a group. So because there were 2 groups on 2 ones only, we have make already 1 group. Khalas, we did not leave any ones outside. So we have combined. Now time to read the function from K-map. So how we will be reading this one? Because this is one group only, so we will be receiving on one product term. How you will be reading product term now? Check from the row wise what is common to this group, which value of the x is common for this group. So we see here this is 1 is corresponding to x and 0 is corresponding to x complement. So what is common from the x side when I am reading this one? Any row wise, it is x or not to this group, complete
Yes.
group?
Yes, X.
X. Now similarly you have to check from the top, yani column wise, what is common column wise,
Z.
which bit is
Z.
common? Definitely Z. Why? Because the second bit is 1 is common to both the ones, this one and this one. What is common? 1. The rest, the y value which is 0, this is 0 here, this is 1 here, yani it is not common, it's changing. So we will not consider this one. All right. So 1 is fixed, 1 is fixed, yani 1 is common and 1 is correspond to z. So I will be writing xz. My function is reduced and it is the reduced function f is equal to xz. And you can see I apply the basic rule and I got also the same answer. It means by using K-map, we are also receiving the same answer. All right, guys. So this is the way. Now, I will try to give you more examples and you will be learning in more detail. Okay. So I'm removing this one and then I will give you new example. So let's say the example, new example is, I am giving you a function f is equal to xy plus x y complement z plus x complement y complement z plus x y z. Question is simplify the function using K-map. This is the question. So what should I do first? Now tell me.
The first term, it had z. We should add z, right?
Make it canonical.
Yes, we can make it canonical. Absolutely right. Because in order to use K-map, we should have minterms. But we cannot get the minterms because this is a standard form. So what we need to do, I have to bring here z first. Right, absolutely right. So this will be x, y, z and x, y, z complement. You can do that yourself. I am just writing short because I know how to just implement this one. Okay. Then after bringing this z, we will be checking, is there any repeated term? You will see the first one and the last one is repeat. Am I right?
Yes.
Okay, so we need to consider only one time. You know the rule, right? So we can ignore one and we can ignore this one, for example, and we will be saying this is our so min terms will be like 1 1 1 1 1 0 1 0 1 0 0 1 bus. So sum of min terms we write like that. So write in order 1 5 6 7. Now to now clear girls, everyone?
Yeah, clear.
Okay, now time to draw the K map, put the entries and on. Okay. So now I'm drawing the K map. This is the K map. X here, Y here, 0 0 0 1 1 1 1 0 0 1, and this is 0 1 2 3 4 5 6 7, the address of the minterms, right? Now look what are the minterms. So 1 is here, 5 we should be here, 6 should be here, 7 should be here. Okay, so I have places all the minterms. Now time to make the groups. Now look, there is a rule when you are going to make groups of ones, you will always combine the adjacent ones. Adjacent ones. Yani if something away, there is a break, we cannot. So adjacent ones can be combined in a group. You can make the groups either horizontal or vertical. You cannot make a group which is diagonal. Means I cannot make a group like that. Keep in mind. Diagonal not allowed. Only what I said, horizontal or vertical we can make. Now, so if we look the way, what is the larger number here? We have 4 ones here. So larger group which is possible, that is 4. But 4 we cannot make here. Why? Because we did not have any end here. If I have entry here, I can make this group of 4. But it is not there. So we cannot have this one basically. So in this situation, what we can do, the maximum group, if cannot be 4, so less number any 2, we have a group of 2.
Yes.
Yes.
We can have a group. So which one could be possible? This one is okay. Group of 2.
Yes.
Right?
Yes.
And two is still remaining. We can make this group also.
Yes.
Right? So we made 2
Yes.
groups. So in my solution, there will be 2 product terms. Just read the solution. Check the blue first. So when you are checking for the blue row wise girls, you will observe that for this first entry, yani this entry, first, the value of x is 0, which is x complement. And for the next one, it is changing to x. It means there is nothing common for this blue group from the row side, because the value of x is keep on changing. This is 0, this is 1. Nothing common x wise. Check any row wise. Check on top. So if you look, so 0 1 is common to this complete group. So 0 is corresponding to y complement and z is simply 1. Clear with this one?
Yes.
Now plus sign. Why plus sign? Because we have one more group. So this will be correspond to that one. Now look for the red one. Red, yani look for first row wise. So if you check from row wise, you will observe that the value of x, which is 1, is common to complete, common to complete group. So it means what is common? X. And from the top, what is common? We have to check from here.
Why?
So
Why?
you see, yes, absolutely right. Y is common. So that's it. This is my solution, guys. Easy. This is my
Yes.
solution. This way I can simply find the solution. All right.
Doctor, you can again how
Yes.
write a solution?
Yes. Why not? Just wait. I'm giving you more examples. So I am coming back, going back to my laptop, and I will be giving you more examples from the laptop. So just a minute. I am sharing my screen of laptop to you. Okay. So because here I already made a blank. Can you see this blank map now? Just a minute. Now.
Yes.
Okay, so it will be easy inshallah, because I can just fill entries here randomly and explain to you. So we can have any function, any minterms, I can give it to you, and you can check, okay, this is there. So let's say the entries are like that. We have somewhere, we have one here, we have one here, okay, we have one here, we have one here, we one here. Let's like that. Okay, now I am asking you combine them. The minterms is given. I am assuming that a function is given, and these are the minterms 0, 1, 3, 4, 5, 7. Now you have to simplify. So first of all, you will make this one and draw that one. No need to make the groups. So while you are making the group, again, as I told you, you will look always to have a larger combination. So tell me, which larger combination is possible? 8 is possible? No, because
No.
we have only 6 minterms. But 4, yeah, 4 is possible. Which will be this one, midterms 0, 1, 4, 5. Am I right?
Yes.
This one, right? This one? Clear?
Yes.
Okay. Now we have 2 more ones which are uncovered or not a part of the group. So we have to combine them as well as per the rule. So the very first rule is that always try to have large group. This is the prime aim. So in this regard, when you if you because your prime is to have a larger group. So for this purpose, if you need to reduce one which is already a part of another group, you can reuse it, no issue, as many times as you want, as long as you are able to make a larger group. So for that purpose, if you look this M7, this single one, okay, so if we check this single one, rather than just making a group of single one, we will be trying to make a group of 2, because we will be using M5 here. Okay, so we can use M5 here, and we can make a group of M5, M7. So let's say this one, M5 and M7. Okay, there is a delay or what happened? I try to make, yeah. Can you see now, guys? This group, M5, M7.
Yes.
Okay. So because I told you, always look to have a large group, and which is possible this way. So that's why I use it. And I can reuse as many times as I want, as long as I can make a larger group. Now you see M2 is remaining now. M2 is alone, single one is remaining. So here a new rule come. You can combine the adjacent one. This is the rule. Side by side, you can also combine corner to corner ones, as long as they are in the same row or in the same column. So by this rule, what I understood, I can make this one, and in the same line I can also take the another one. Yani this one is possible, and this one. Yani M0 and M7 both are possible. This one also. Now see. So I am reusing M0 for M to make new group. This is like corner to corner group. Now I am going to write my use functions. Now you can see the student who asked me how to read it. I am going to write the function. So f is equal to f equal to. So let's go for the blue first. What is common for the color? X direction. X or X complement? X only. And from the top, what's common?
Z.
Z. So it will be XZ or XZ. Now, plus, check for yellow color. Column row wise first, then column wise. So X complement is common, X naught, and from the top, Column
Z
wise, what is
complement.
common? Z complement. Absolutely right. Z complement. All right. Now what is remaining? The red color group. Go for red color group. So for the red color group, girls, as I mentioned earlier example also, if you have complete column filled with the ones, complete columns filled with the ones, see, this one is there already, one is there already. So you will not getting anything common row wise because you see the value of x is 0 here, 1 is here. So it's changing. So I will be not getting anything common row wise. Okay. Now check column wise. What is the possible? What is the common, column wise? These two. Because this is covering a red one. So if you look here, this 0 bit, yani y and z. So z is changing. For the first column, it is 0. For the second column, it is 1. But y is 0 for both the columns, first and second column. Yani for the red, we are focusing on the red group. So what is common? Y complement. Correct or not? Y complement.
Yes.
Clear? Okay. So this is our answer, bus. This is our answer. This is the way. Have you noticed something? We make 3 groups. 2 groups are basically group of 2 ones. The third one is basically group of 4 ones. If you just focus there, you will see the smaller groups which are 2 2. They are giving me 2 literals, 2 literals. The one which is a group of 4 is giving me only 1 literal. It means larger the group, lesser the literals. And our aim is to reduce the function. That's why our prime is to have the larger number of ones in a group. Keep in mind. For that purpose, we want to use the number of ones, which is already a part of another group. We can reuse as many times as we want. All right, guys. So we'll continue with this one. I think it's better to have a prayer break than start. Is it okay?
Okay.
Okay, just have a break of max 10 minutes. I will try to, if you finish early, then we'll be rejoining. Okay, so just, right. Similarly, we can have also a number of examples. Let's see this one. Let's assume if this is our entries. So I am giving you a few random entries again. Like that, here, 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 and let's say like that. For example, right now, this way. So now, how you will be making the groups? Tell me. Maximum always, first thing, should be power of 2. For 4,
46.
this one, complete row.
Yes.
Yeah.
2 ones are remaining, not an M3.
0 with 4.
I'm not an M. 0 with, and it's not, it's 2. This is M2 actually, M2. Yeah. So 0 with 2. What is your first prime aim? You must have the maximum number of in a group. Okay. So if you go for 2 and 0, so you will be having group of 2, right?
Yes.
And I told you, you can use the ones, which is a part of another group. So we can use these 2 ones from that side, and M2 and M6, this one, which is possible, and this 2 from that side, which is also possible. This one, M not M, this one. Clear now? Because this is main group. So I can reuse M4, M6 midterms. This is the way. Okay.
Doctor,
Yes.
it's true both ways.
Sorry.
It's true both ways, or or no?
I did not hear it properly. Can you repeat your question?
Universe cutting also. خلاص. Okay.
You understand? Okay. So guys, is clear now? This way. Now you create the function as the same way. So for the blue color, you can check first column row wise. So if you look row wise, X is common because it's a complete row entry. As I told you, it is a complete row entry. When this is the case, when you have complete entry, nothing will be common column wise, because if you look column wise from the top, the value of Y and Z will keep on changing. Basically, will keep on changing. So in this situation, we will be not getting anything common. Even you can check. This is Y0, Y0. Here is Y is 1, and Y is 1 here in the next. So this is, once we have all the ones filled in a row, nothing will be common from the top column Y. This is, so we have only X. No, plus. Go for the green color. Okay, so when you look for the green color, you will again observe that the column is completely filled once, this one and this one. So when I try to get it common from this side, I will see that value of X is changing, 0 and 1. So nothing is common this side. Okay, so nothing common. But from the top, we can see something common to this first column and the last column. It is corresponding to green one, right? So when you see this one, you will see Z complement is common to both first column and Z, correct?
Yes.
So this is my function. This is my function. All right. Okay. One more example like that. Here now all, and I'll give you more example. Okay, it's clear. All right. So let's have some entries. Random entries again. I am filling like that. 1 1 1 1 1 1 1 1. See, if all are filled with ones, all midterms are present in a function. Now, what is the maximum group of ones possible in this situation?
8.
Yeah, absolutely. 8, yani all ones are there. So in this situation, when you have this one, so what will be your function? Function will always be 1, because whatever your input combination, all the time you are getting output 1. So once you have completely filled K-map, the function output will be 1. Alright. This is about the means the minimums are given to you. You need to fill it. You need to find this one. Now I'll give you example of the don't care conditions. Like I am giving you a question and asking you to simplify this one with the help of don't cares. So what are these and what are don't cares? Let's see. So I have given a function. For example, f is equal to summation 0 1, okay, and let's say 0 1 2 and 5 and let's say bus, and plus D. Stand for don't care. D stand for don't care. We have these don't cares 3 and 6. We again 3 and 6 don't cares. Okay, so we have asked you to simplify this function. So I think I entered here with D don't cares. So how to solve the question using don't care conditions if it's given. So first of all, very first thing, you have to fill this entry. So this is a place of 1. This is another minterm. This is another minterm 2. This is from 5. I have this one. I have also given the don't care conditions, girls. So I will fill don't cares also. So don't care is basically filled in the map with X. So 3 will be my one don't care. Another is will be my don't care. All right. Now So these don't cares, basically what are the goal of the don't cares and how we will be solving the question with the help of these don't care girls. So it's like that, if don't cares are helping you to make the larger group, so you will use them in your group, else you will leave them as it is. It is not necessary to combine them in a group, or you will try to cover in a group. No, if not helping, leave them. So so the very thing, you will try to have a larger group. So which larger group possible group? It was possible to, what is possible now?
First row.
Yeah.
First row. Yes, so absolutely right. We are saying the row, yani we can have the first row as a group, because it here don't care condition is helping me to have this larger group. That's why I will be using this one. So right, absolutely right. This is one grouping. Now, still one is uncovered. We have to cover an M5 entry somewhere. So now tell me, how can I make a group for this M5? What is the way?
1 with 5.
Absolutely right. 1 with 5. 1 with 5. So we'll be going for 1 with 5. Now, one care condition is there, M6. So as I told you, we are not going to care of these don't cares. Leave them. If they are not helping me to make a larger group, khalas, leave. We will be not looking this one. So that's it. Okay. Now you read your function, you can write your function final like that. For blue color, X complement only, and nothing common from the column wise. I told you. For the yellow color, nothing common from the row wise, but from the column wise, we'll be getting Y complement Z. This is my final output. Clear, girls?
Yes.
So this is a solution using don't care conditions. Using don't care conditions. Okay, now one more interesting question for same way question you can attempt with the same way. But the point is you are not going to cover the don't care condition if they are not helping you to have a larger goal. Otherwise, leave them. So now let's move to next question. Then I'll ask you to solve with the help of okay. So I am giving you this function. Let's say function is given f is equal to summation 0, 1, 7, 6 plus care 20. Let's say if they are, if you have mints there, the min terms cannot don't keep in here will be different. They cannot be like the mints. Now this is so simplify question is that simplify the function as product of max terms. And on max terms, you will say product of sums. Product of sums. So product of sums, yani POS. No? POS. This is my question. So I have to simplify this one. POS. Product of sums. As we know that this is minterms, girls. If we have minterms, then my function is sum of products. Even for the last examples, whatever we got the solution was basically standard sum of products. But now I have given minterms, and now they are asking me to have the solution in product of sums. So how can we do this one? Because they are opposite to each. Know that one. Yani minterms are complement of maxterms, or maxterms are complement of minterms. So if you wanna solve this given solution which is in sum of minterms as a product of sums, so what we need to do? First, we need to have the maxterms. And do you know how to find the max from the given function? This is minterms.
Yes.
Yeah.
So yeah. So please tell me, how can I find the maxterms?
The product
Two,
is
So function, yeah, pi
two,
will replace
three.
by sigma will replace by the pi first of all right guys, sigma will be replaced by the pi. And another thing, why you are converting don't care function, so your function will be f is equal to, which is already pi is there, okay, after pi in the bracket you need to list those numbers we are not as a maximum in terms there. So of 0, 2, and you know 2 is basically don't care girls. So those don't care, they will be same for both function. Don't care could not be like maximum as well. So the don't will be same. And those are don't care for the given function, they are going to be same for the another function, which is maximum function. So D here will be same. Here 2.5 will remain same, no change. Okay. Now tell me what are the maximums. So if not 0, yeah. What's Rojan? This one. And voice is not clear, huh? Just a minute. I'll try. Okay, it's not clear. Okay, just a minute. So now can you tell me what will be the maximum if the don't care conditions are remain same? So in this type, 0 is already min term, 1 is min term, and don't care are 2. So 2 cannot be maximum. What will be the maximum now?
3 and 4.
Yes, right. Absolutely right. Next.
4.
5 is there already as a don't care. It could not be. So 3 and 4 only. Because 5 is 6 is min term and 7 is min term. So there are only 2 max terms, which is 3 and 4. And 2 don't cares will be 2 and 5. Am I right? Is it clear to everyone?
Yes.
All right. Now, so how we are going to put these entries in the map? This is interesting and important because we have function which is basically in max term. Rather than putting ones, we are going to put zeros in the K-map. Clear? Because min term and max are complement of each other. That's why. So I'm going to put this one in the function. Now see. So in the K-map basically. So 3. So 3 is there. Min term, another max term is 4, which is there. So I have put 2 max terms, which and 4. And now we have given 2 don't care. We are 2 and 5. So put that one 2 and 5 as well. 2 is here, girls, and 5 is here. All right. Now we have to make the groups. Okay. Now help me out to make the groups. Group of 2 possible, considering the this one don't care condition. Yani,
Groups of 2.
this is, yeah, this one is possible. Another one, this one is possible. Yani 3 and 2 and 4 and 5. We can make them these 2 groups. All right. So after making these 2 groups, next point is to read the function. And this is very important. While you are reading the function, girls, it is not going to read as a f. It's going to read as a complement of f, because while we convert the min term into max term, basically this is now function become complemented function. So when we will be just simply just writing the function, so it will be like f is equal to, I'm writing F equal to, just read for the green box first. When you read the green one, and it will be complemented, as I told you, it will be the complemented function. Yani it will be F complement, which we are reading now. So it is F complement.
X complement.
Is it F complement, right? Is equal to X complement. Okay. Then what is
Z.
common from the top?
Y.
No, Y complement. Yeah, Y complement. Now less. What next? For the red color now. So no, sorry. What we write this one for the green color. I want to write first for the green. So I have to check this one while we are doing for the green color. So it's different, guys. So it is like X and from top Y complement, like that. Now look for the red color. It is basically a red group. So it is what? X and Y. Correct this one?
Yes.
Okay. So this is our complemented
Yes.
function. Now what we need, we have asked to find the solution as a product of sum. Is this product of sum? No, this is sum of products basically, and this is a complemented function. So what I will do, I will take complement both side, girls. What I will do, I will take complement both side and I will apply the De Morgan theorem. So what I will be going to do, I'm going to take the complement both sides, and take complement this side and take the whole complement of this function. Okay, then apply De Morgan. So while I will be applying De Morgan, you know that F double, what I will be getting? Double complement. F
No
complement, then complement. It is removed and simply F. Okay, now, and I told you while I was explaining this De Morgan theorem, this is gonna be considered as a single unit, another one is going to be considered as a single unit. So I will be applying De Morgan like that. In the bracket, X, Y complement, whole complement, plus will become dot. Then I will be writing again. What is next? X complement, Y whole complement. All right. Now apply De Morgan again one more time in the brackets individually. So it's gonna be what? What is going to be? X
X
complement
complement
Plus Y.
and
plus
plus Y. Correct? Yeah. Dot.
X plus Y complement.
Okay. So it's gonna be X plus Y complement. Now, if you look this one, is this product of some solution or not? Because we have some sums, then we have product. So sometime the question can be asked this way, with just to just check all your knowledge of sum of min terms, product of max terms, like. So this is the solution in this situation. Okay. Example is given also in the slide. When you read, it will be clear to you, inshallah. Okay. So this is about 3 variable map curls with the don't care conditions, and even if you want the solution in product of sums, we can do this one. Provided, keep in mind one thing, don't cares are gonna be same. Don't care cannot be min terms and max term. So the which is the don't care which is given for the min terms is going to have same for the max term, basically. Right? So
I have a
just move.
question.
Yeah, please.
Why did we switch them? Why did we say X instead of X, the negation of X?
Okay, just a minute. Can I go back now? Sorry, I cannot go back. I just remove it mistakenly. Okay, we switch because in the question it is asked that find the solution in product of some form. Question said find the solution in product of some forms. because the solution which we got earlier, that was sum of product. If you just go for any solution in this slide, let's say if I just show you the previous solutions, where are that? We have some solution, just a minute. I don't know, let me try. Yeah, see this, can you see this one?
Yes.
Check the solution. Check the solution. Is this SOP a sum of product or product of sum?
The sum of products.
Sum of product, correct. But here in my question, I asked find the solution in product of sums.
Okay.
In product of sums, correct. So what I did, I have given minterms. I got the maximums from the rule which we know. After getting the max terms, I put the zeros for the max term in the K-map. Then I combine the zeros there, use the same don't care conditions. When I will be combining zeros, my function which I will be writing as a solution, which is going to be. So I receive function as a F complement. Then what I did, I applied the De Morgan theorem, both the side, so it's become F, and my solution converted into product of sums. That's why I did this one.
Okay. Thank you.
Okay. All right. So this is about that one. Now, okay, I'll be moving to just a minute. Okay, so this is some more solutions which I have already covered. You can see now coming to this is already covered. Now, for example, see this one. This question may also come like that. So here you can see this is a standard form. Basically, we need to convert this first into canonical form, bring all the literals. After bringing all the literals, we will be finding the basically some minterms. Then we can just place it and simplify. So the examples which is in the slide direct is very simple. Now moving to towards the next one, which is basically the 4 variable map. So 4 variable, yani 2's power 4, 2's power 4, which is going to be 16. So we are going to have 16 squares for the 4 variable. And how it will be, it now 4 rows, 4 column. So let's say it is WX, this is YZ. So WX will be their combination will be 0, 0, 0, 1, 1 as it is in gray code 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. It's like that. And now we can check the address of each minterm entry like that. It's better again if you can memorize. I will try to explain you 1, 2 times, then you will be knowing. It is like that. 0, 1, 2, 3. See this. 0, 1, 2, 3. 4, 5, 6, 7. The down one now. 8, 9, 10, 11, 12, 13, 14, 15. So this is the way. These are the places of the minterms. So we will check the function. What are the minterms given? Just place that one and then combine them. Okay, this is the way. So let's have an example. Now see this one. So this is the question for you. So you can see W, X, Y, and Z, 4 variables are there. It means we have to have 4 variable K map. So I can draw a 4 variable K map, which is gonna be like that. 4 rows, 4 columns, as I mentioned earlier. You can make like that. It's gonna be W, X, Y, and Z, and their 0, 0, 0, 1, 1, 1, 1, 0. Values will be 0, 0, 0, 1, 1, 1, 1, 0. And the minterms entries, as I just told you before, what it will be like 0, 1, 2, 3, 4, 5, 6 and 7, 8, 9, 10, 11, 12, 13, 14, and 15. So these are the addresses of the minterms. Now check the function. What are the entries you have given? Minterms are given. Because suspicion is there, it means these are the minterms, not max terms. Okay, so 1, so 0, 1, then next is what? 2, which is here,
2, 4,
then
5,
5, 6, 8,
9,
9, and these one. Okay, so we have filled all the entries. After that, again the same rule which I explained to you, try to have a larger group. So now look, what are the larger group possible this time? What is the maximum group which I can combine this time? Just for that.
8.
It's gonna be 8. Okay, just check if we can have 8. Okay, let me just erase some of them. Okay, group of 8, absolutely right. So we can have a group of 8 basically. So all right, so group of 8. So which group? First 2 columns, am I right?
Yes.
This one, the first 2 columns, group of 8. Now 3 ones are there, we have to cover these 3 ones also. Now how can we combine them, considering that we are going to have a larger group, provided the group could not be other than the power of 2. Now
Group of 6.
2 and 6 and 14 together.
The first column and the last column,
2, 6,
first
0,
column,
4.
but only
okay,
6.
6 and 2 with 1, 2,
0 and
4, 5.
6 and 2 with
0 and 4.
no, how it could be, check again.
2 and
I'm
6
writing
and
the loop.
14.
With 0,
2 and 6 and
with 0, 4, and 12.
2, 6 with
0,
14.
4. See. You know that I told you you cannot have group of 3, cannot have group of 5, 6. I already told you 7, 9, 10 not allowed. Why not allowed? Because they are not the power of 2. I told you group could be 1, 2, 4, 8, 16, and so on. We cannot have a group of 6. We cannot group 7 like that. So if not 8, another group could be 4. Clear?
Yes.
So
Doctor,
think
2 and 6 with the 4 and 0.
absolutely right. Absolutely right. Yani these 2 from the right side and these 2 from the left side, which is possible. I already told you. This is one group. Now still we have one remaining, and I have to cover this one as in a group. So what is the possibility now to cover this one?
14 and 12.
14.
With 2
14.
and
12.
See, if I go for 14 and 12, it will be group of 2. And your prime aim is to have a larger group.
Doctor,
14 and 6 with the 4 and 12.
can have 6 also.
Yeah.
3
Yeah.
on the
So
right
we
and
can, we can reuse, na? We can reuse 6.
yes.
Yani we can have this 2 from the last column and these 2 from the left column. You can reuse as many times as you want, provided you are forming a larger group. Am I right now? Clear this point?
Yes, clear.
Okay. Large group will was less number of letters or minimize solution. That's why. Okay. That's finished now. Just read the function. So it's very simple for the reading of the function. You can see the blue color, because blue color having is complete column tree. So we are not going to have anything common from the row wise, but we will be getting common from the column wise definitely. So check what is the function in this condition. F is equal to
Y
For the
complement.
blue color, only y complement. Absolutely right. Only y complement in this equation we will be getting. So it's only y complement. All right, y complement. Now let's go for the yellow color.
Z
So
complement.
check. No. For the first check what is common from the row wise.
Nothing common.
Why?
There
Oh,
is
yes. W.
W complement.
W complement. Yeah. First check row wise, then check column wise. Okay, and then here from here Z complement. So W complement and Z complement is the related for the yellow color. Now black color. X.
Z complement.
Z complements. Correct. Now can you see what is the larger group here? Group of 8. So because this group of 8 I am having in the solution single literal, but group of 4 is giving me two literals. I told you larger the group, less number of literals. That's why we always try to have larger group, try to form a larger group. Okay, by the way, now these basically groups are also called as prime implicants. What are they called? Prime implicants. So how many prime implicants I have here? I form 3 groups. So I have 3 prime implicants. All right, girls. Okay, let's see. I'll give you more examples quickly of this one with a blank page. Now, so I have this blank. I will be filling some entries and I will be asking you to combine them. Okay, so let's. These are the entries. I have 1, 1, 1, 1, 1, 1, 1, 1, and I have this one. And yeah, for example, this is the way. Now tell me, how can I form the groups and what will be the, you can say row, column, something that I will recognize. Large group,
the first column
first
with
priority.
the last.
Yes. A.
First column with the last column, yani 4 from left, 4 from right. Correct?
Yes, right.
This way. All right. Now, what else I can do?
The third row. Fourth.
Third row, complete row. Right? Group of 4.
Yes.
All right. Good. Very good.
The first row, 3 and 2 with the last row.
Wow, mashallah. Very good. Yani group of 4. Right?
Yes, group of 4.
Absolutely right. Yani these two and these two. Very good. Mashallah. You are getting now. But you know that how to read the function, right? So you can read the function and write that. Okay. Let's have some more examples with the different entries. So again, we have here 3 prime implicants because of 3 groups. Okay. All right. So now tell me about now. These are the entries.
First column.
First column, right?
2.
First column. Now
The first row and the last row.
first row and the last row. Okay, I am going to tell you one interesting thing. Okay, you will learn a new thing. If you have a corner once in once in all 4 corners, you can combine them together as well. If you have once at the corners of a square, you can combine them as well. Yani, according to that, what I am saying, this one from this corner, from this corner, from this corner. they can combine together as a group, single group. 4 corner entries, new thing for you. This is possible. Clear this point?
Yes.
Okay, so while you will be reading this one, you will check what is common to first row, what is common to last row. So you will see that x complement is common. So x complement, and from the top, first column, last column, what is common? Z complement is common. So this is for the blue color, you will be getting like that. For the red one, what is the for the red one? Simply y complement, z complement, like that. Now, what are remaining now? Cover them as well. So 3 ones are there. We have to combine them.
Row 2
So
and
it's very
3.
simple. Combine them as a this one good this group and combine this group. Khalas. Clear?
Yes.
All right. So this is the way you can simply them. So how many prime implicants are there?
4.
4 prime implicants. Very good. 4 prime implicants. Now girls, I'm going to teach you the new thing here, essential prime implicants. What? Essential, just a minute. Essential prime implicants. You know the meaning of essential? Necessary, important, or like that. So this is yani prime. I'm talking about the implicants which are necessary or which will be present in your solution. Say I'm giving you this example. Just please focus. Important topic, girls. I have the entries of this. Okay. Now I'm asking you combine them. Mega groups. So you will be making like that. Correct?
Yes.
Then, okay, I'm using green, no problem, use green color. This one, and the last one will be like that. We have covered all, right? This with the green, with the last one, with the no. So let's write the function. Let's write the function. Function f will be starting from the yellow. So when I look for the yellow, it is basically what is common row wise. You will see w x complement, and from the top y complement plus, okay, w complement y complement plus, look for the blue color. So for the blue color, what is common?
W.
Row wise w, and from the top
Y
y complement, yes, plus. Now for green one, x y
X.
z, you can check y and z, the top, okay? From the top. Now the red color, for the red color, w complement y z complement, check it. Okay, so while I was making the girls, anyone think make a group in a different way, or you think this is the only solution? While I was making the group, or do you think is there any other to make the groups?
Yes.
Okay, what is this?
Cell number.
First one like that.
Horizontally,
Second
not
one,
vertically.
very good. So you are thinking like that. One horizontally. Okay, one horizontally. So if it is like that, okay, what next? Horizontal. This next one also horizontally.
Can be, yeah.
Yeah, and the last one also is going to be, let's say, the blue color horizontally. So one student just did in a way left side, another student try this one. Okay, let's write the function for the solution also, girls. Write the solution for this function also. F is equal to, start with the blue and we'll be going up. So when we go for this one, so it's going to be W x complement, and from the top y complement, W x complement y complement, plus look for the yellow color now. So W x z. Am I right? W x z. W x z. All right. Now for the green color.
W complement X.
And y. All right. All right. Now the red color. W complement y z complement. Clear?
Yes.
All right. So we have find two solutions by the two ends, and now we are going to have a close look here of the essential prime implicants. My question here is, find the solution of the given question and find the essential prime implicants. You know that all are prime implicants. If you look the left side, we have 4 prime implicants. If you look the right side, we have 4 prime implicants. Can you check the number of terms? Are they same or not?
Yes, same.
In both solutions. So both solutions are accurate because both solution can be implemented using 4 and plus 1 OR gate, like that. I'm going to fulfill the simplification criteria. But my question is not like that. The question is, what are the essential prime implicants? So essential prime implicants or necessary or important prime implicants are those prime implicants which will always be present in all the solution if you have multiple solution. So in this case, we have multiple solution. So we will see here what are the product terms which is common to both the solution. Can you please check? The first product term both the solution is common or not?
Yes,
Yes.
Common, right? So this is common, this is common. It means is that it is a essential prime implicant. It will be there all the time you have multiple solutions. Check the second product term. Is this same or change?
Change.
It is not an essential prime implicant. It is prime implicant, but not essential. Check the third term.
No, it's
Different?
No, different.
So it is prime implicant, but not essential prime implicant. Check last one.
Same.
It's
The same.
Same. Same. So if I ask you a question, girls, simplify the given function and find the essential prime implicants. So you don't need to write a complete function. You can find complete function, but I am looking that you will be saying, okay, we have 2 essential prime implicants, and these are Wx complement, Y complement, and another one, teacher, W complement, Y is complement. So this is the reported answer in this situation. Is it clear to all of you? I'm asking you essential prime implicants. What are the essential prime implicants? So 2 essential prime implicants you can write. We have 2 essential prime implicants. These are like that. Is it clear to everyone? This is complete solution. But and if I ask my question, find the essential prime implicants. So, okay, you can write the complete expression, but you need to tell me what are essential prime implicants. So there are 2 essential prime implicant. You have to write, we have 2 essential prime implicants, and are these one like that. Clear?
Doctor,
How to report answer? Yes.
we have to solve it both ways in the
This is
exam.
the point. Yeah, this is the point. I'm going to that point. Now, you are not required to solve all possible ways, though I will tell you from the left side solution how to find essential prime implicant directly without solving all possible solutions. Yani, I will ask, tell you how can you give your time. You're not supposed to solve all the possibilities, then find the essential prime implicants. You can directly find the essential prime implicant from the solution itself. I'm going to tell you now. Clear? This is okay for first, how to report your answer. This is okay. Now I'm coming to the point, how to find essential prime implicant directly from one solution only. Am I clear too?
Yes, clear.
Okay, so now focus on left solution only, left side. So look here, left girls. We have 4 prime implicants. I am trying to find what are essential here. So how I will know? Check the red color first. Focus on red color. So this is a group of 2 minterms. I have 2 minterms here. So I'm going to use the black color to hide you what I'm trying to do. You check with this minterm. Is this minterm can be combined any other way?
Yes.
On the red group, folks, if you have to focus red group only, red prime implicant only, and you check. There are 2 minterms. So you check the first minterm. Can we combine any other way? You said yes. Correct?
Yes.
Okay. Now check another one. Can you combine the first minterm of this column any other way other than the one which is red color formation?
No, we
Can you
can't.
combine this? Provided you will be not making a group of 1. You will be not to make a group of, you are not, the very first thing that you will always going to make the larger group. You cannot say, no, doctor, we can make a group of single. No, 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 no. Provided you will be always looking to have a larger group. So what we find that this minterm below one can be combined, the next one cannot combine. So the rule is that if in a prime implicant or in a group, if you find any minterm, I am repeating again, in a group or what we call prime implicant, if you find any minterm cannot combine another way or cannot combine with any other group, only single minterm, if you have only single minterm in a group, that cannot combine with any other group. So that group become essential prime implicants. So in this group, we have 2 minterms. One can be combined, but another cannot. You need to find only a single minterm which cannot combine any other. So what I find in this red group, that the first minterm cannot combine with any other group. The solution is the red will be always there. Getting point? So this become essential prime implicant, EPI, because of this minterm, because of the first minterm. Because the first minterm cannot combine any other way except the red group. That's why. Look for the green color. It will be more clear. Green color. So when I move to the green color, you will see that focus on the first minterm. Can you combine this midterm any other way other than the it is combined in the green one?
Yes.
So check this one
Yes,
first.
I can.
Yes, we can combine with the neighbor right in any horizontally. Okay. Now check the another midterm.
Yes,
Another midterm. Can you combine any other way?
Yes.
yes,
Yani both midterms can be combined different ways.
yes,
non-essential prime implicant. Clear?
Clear.
Okay, because both of them can become different, non-essential. In short, I can say any non-essential. Now focus on the blue color. Check the first minterm. Can you combine other than the blue, the first minterm of this group?
Yes.
Rather vertical in and blue, we can also combine this minterm as a horizontal with the neighbor. Okay, check the next one also.
Yes, I can.
Right? So it means both can be combined different way. So it's gonna be non-essential or
Non-essential.
clear? Non-essential. Yeah,
Yes,
because
yes.
there are possibilities that both minterms can be combined. Now look for the yellow color. When you focus on yellow color, you will find the very first minterm, which is
I can.
the last. Okay, you cannot combine any other way other than the this yellow color. So what we are looking? We are looking for only single minterm which cannot have other way for the combination. So in yellow, again, we did not find any other way to combine this particular minterm. So because of this minterm, this prime implicant become essential prime implicant. So what I find here, two essential prime implicants, the yellow color, the red color. Hope it is clear to all of you. Clear, girls? Or should I
Yes,
give you
I
more
did.
example?
No, it's clear.
Should I give clear na? So okay, let's quickly, I'm going to give you one more example and you have to tell me what are the essential prime implicants. So let's go for that. Just remove this one all, and I'm just putting some please around you. Okay, so this is like that. For example, if you have these and these, okay, so for these entries, girls, what question is that again? Solve this function and find the essential prime implicants. So you will solve it first. Hope it is easy for you to combine and make the groups as I explained to you already. So we have 4 corners we can make group, correct?
Yes.
And now just make a green for this and just have middle blue, which will be covering this. Green and blue and yellow. So we have here 3 prime implicants. I think blue is just maybe making some delay. So is there, right? So we have cover all, and I can also write the function. So I'm writing the function. The function is f is equal to, for the yellow, it is gonna be x complement, and from the top z complement. Plus for the blue, I can say x, and from the top it is, for the green it is gonna be w, and from the top z. Okay, I just write the solution, but my question is find the essential prime implicants. So what are the essential prime implicants now? So again, as per what I explained to you, first look for the yellow color and try to find, is there any minterm which cannot combine any other way?
Yes.
We combine this one another way other than no,
0 and 2.
because we cannot compromise with the grouping. It is a part of group of 4. You cannot make a group of 2. Let's say the first entry of that column and the last entry of that column, and say teacher we can combine as a 2. No. Always we have to check the larger possible group I make already. So this one not have any other. It means is that for this one as well, even for the next one, the column first entry, this cannot also. Okay. So it means this one, the first one is essential prime implicant, EP. Correct, girls? Now check the blue one. Check the blue one. So for the blue one, you can see it is all combined to two ways. Correct or not?
Yes.
It is a part of two groups, yellow, this one, blue and green. It is already a part of two. But what do you think? Can we combine upper two any other way
No.
other than the blue color?
No.
There is no way. And I have to find only single minterm which cannot combine any other way. But here we have two minterms which cannot have any other solution. So it means this is also EPI as the primary. Now check for the green color, girls. Check for the green color. So for the green color, just please see. So here, if you this minterm, can you combine this minterm any other way below two minterms?
Yes.
Yes.
Which what is the way?
Last row.
Can we make a horizontal this one or not? Any complete row entry of this one, rather than having this green one, we can also have this one. Correct?
Yes.
Correct. So in this situation, we did need to make this one. So basically the point is green is non-essential. Why? Clear? Getting point? So we can have another solution. So point is that we cannot, it is not necessary to have this one only green. We can form the black as well. So the below this one, next one can be combined any other way, and upper two is already combined with the blue one as. So once I make the blue and the black color, I did not the green one. So green prime implicant is non-essential because in place of this green, I can also find the solution as a black one. So the last one is non-essential. NEPI, non-essential prime implicant. Clear, guys?
Yes.
Clear.
Okay, so this is non-essential prime implicants. So this way we can find, and question is asking, but so what are the essential prime implicants? So you have to find it, tell them. So this way we have covered all these prime implicants, essential prime implicants. Let's see what is remaining now. Yeah, so few more examples are this. You can also check some examples, and you see for this end we have the essential prime implicants. We have 4 solutions, but in 4 solutions B complement D complement, it is common. It is common basically. So it means is that it is essential prime implicant and will always be there in my solution. Okay, this is again example of essential prime implicant. You can check. Now this is process of converting SOP and POS. I have covered that one, girls, already. Product of sum simplification. So I told you we need to first extras and need to enter zeros in place of ones, what I explained, and then apply later on De Morgan theorem. So see the example. I have covered that one, so it will be clear to you. So this is the question. For this given question, they are asking you to find the solution as a sum of products and find the solution as a product of sums. There is no care given this time. So just minterms are there. So for the minterm, we place one in the map. I'm going to have in a part A SOP solution, sum of products. For that products, I have to combine ones. So I will be combining one here, girls. So see now, I'll build this one. So these are the groups, three groups, all the solution. So this is sum of production. Now side by side in part B, we have asked find the product of some solution. So the way is that you have to find the max terms, okay, then place the zeros in place of them, and then combine the zeros basically. All right. So these are the zeros which are there. They are basically the max terms. Now the functions which I will be getting, I already told you, we are going to have as a f complement. Why? Because we are combining 1 0 rather than ones. See now, so this is, we are combining them, and just reading function is same way. So now it's f complement function. We have to find solution in POS, product of sums. Now apply De Morgan theorem both sides, and you will be getting your solution as a product of sums. I have covered already this one, right? So this is the way. Now this is the implementation, girls. Both way implementation. It's very simple. The implementation of the function B complement D complement plus B complement, your product. So corresponding each product, you know that will be having AND gate. So we need to have a 3 AND gates. Overall, because it is a sum of product function, we are going to use single OR gate. Another one, it is really product of sum solution. So this is sum, this is sum, this is sum. We need 1, 2, 3 OR gates. Overall, we need a single AND gate. Actually, we are giving here A complement, C complement directly, or we can give by NOT gate, which is also possible. These two different style of implementation. First, sum of product. Another one, product of sums. So all this one I already explained to you how to convert, how to find maximum from the minimums. Simply replace sigma by pi and get this. It is already covered. Okay, what next? This is the solution. I already explained this one. Sum of product and product of sum forms, take the complement and get the solution. Don't care conditions. I already told you about the don't care conditions. These entries are basically like a cross. In this table, you can see ones are telling you min terms, zeros are telling you max terms, and cross is telling you the don't care conditions. So like if it is given like that, summation sigma 137 plus D2 is the don't care condition. Okay. And if you want to find the maximum will be, you will replace pi by sigma, but D2 is not going to be as a min term or max because D2 is a don't care, and don't care will be same for min term as well as max term. So these don'ts are both min and max term. So in K-map, you will be, then you will maintain. You see this one. So we just form the K-map and have to this one and simplified. Now we can implement using one AND gate plus overall one OR gate. So this is the implementation of this function. All right. Now question could be like that. F is equal to given this one and don't cares are given this one. Now simplify. Simple. Just you see we just enter that one and there are two possible solutions. You can see this one. And now please try to tell me, both solution are basically giving you two product terms, almost same answer. Which one is more appropriate? Which one is more appropriate, you think? I should consider the left side solution or the right side solution?
The right side solution.
Why I should consider right solution? What is the reason? What do you think?
Because you use less don't care terms.
Yeah, you're absolutely right. Because in the right side solution, we are using single don't care to form a group of 4. But if you look for the left side solution, we have to use two don't care conditions to make again group of 4. So that is more stable, less stable solution. So we should go in the the more stable solution, using single don't care condition. So this is more appropriate solution in this condition. Yeah, your answer is absolutely correct. Because of single don't care condition using in second solution. All right, just given here this one. Okay, girls. Now next topic is basically, can you give me more 10 minutes, girls? Because today I have stylus, I can draw something. But next lecture I not have the stylus. So if you give me 10 more minutes, so at least I can cover this one part, yani NAND part. What do you think? Again,
Okay.
you are not, all students are, only 19 students are there. I am also recording the lecture. So inshallah, you can, those are not here, they can at least read this one. And this is very important. I must have a stylus. Actually, I have a stylus, so now I can use this one. So important, and based on that, we'll be having at least one question. Do you know about NAND and NOR gates?
Yes.
Do you know these are called universal gates? NAND and NOR are called universal gates. Reason why do we call universal gates? Just guess. Okay, read it. At least you can read it. It's very simple, mentioned there.
Because
It is very simple.
any logic circuit can be implemented.
Yes, absolutely right. Because by using the universal gates, we can implement any logic circuit. Any logic circuit means if I give you NAND gate and NOR gate, you don't need any other gate. You don't need any other gate. You can just implement any function with that one. That is basically the important aspect of the NAND and NOR gate. Sufficient. Look this one now. So this is, we know that not gate, and this not gate, if I am, the symbol of the NAND gate, this is called NAND gate symbol. Two inputs NAND gate I am showing. So let's say if it X, if it is Y, and the output is here F. So I can draw the truth table for that. And what is the NAND truth table? It is going to be XY. It is F there. So 0, 0, 0, 1, 0, 1. What will be the output? Because it is basically what? Not AND. Not AND. So 0, 0 is basically 0 because AND operation is like a multiplication. 0 multiplied by 0 is 0, and because of the component it is gonna be 1, and next one is gonna be 1, next is gonna be 1, last one is to be 0 only. This is NAND gate. Now see, how can I use this NAND gate as a NOT gate? As a NOT gate. Okay, for that, if I combine the inputs, so rather than giving two different inputs, one is X, another is Y, I have this one, and I am giving only single input to both the inputs here. And let's function of this, we know that the function is X and Y. So it's XY complement, you know that one, the function. Okay, just a minute, I'm writing here spaceless. F is equal to F dot Y whole complement. This is not NAND gate. So if I place X and Y together, yani I replace Y with X, both the inputs are X, X and Y. So if I put this one in function, X dot X complement, you know what is X dot X? X.
It's 0.
It's simple X. No. X. X.
Is X.
X. It's X la. So it is what? It is be like that, not? So to this circuit X, what I am getting from this circuit? Getting point or not? Give X, and what I am getting?
X not.
I give X not, so means it is behaving NOT gate or not?
Yes.
This is my point. All right. So that's why we are implementing NOT gate function using NAND gate. See the another examples, it will be clear to you. It is simple now. Another one we are having for the AND gate. And what is the AND gate function? It is like if we have XY input, so it will be X is equal to X dot Y. It will ask you what is AND gate function. It is what basically X dot Y. So I am going to generate that function. So this is NAND gate. Here I am giving the X and Y. So because of this bubble which is there at the here, what I will be getting? I will be getting X dot Y complement. But I did not need this bar at the top because OR gate says gate says F is equal to X dot Y. So I did not need it. So what I can do in place after this one stage, let's as I already explained to, NAND gate can also work as a NOT gate. So I am using one more NAND gate, and another input is gonna be duplicate here so that it can behave like an NOT gate. So here I am giving X dot Y complement. So I will be getting, can you tell me? It will be as an, so it will be giving me a double complement, and because of this double complement will happen, these complement will cancel each other and I will be getting F is equal to, is it correct or not?
Yes.
Right. So how it is behaving using two NAND gates, I am basically implementing the function of AND gate, because AND gate says F is equal to X and Y. So I am giving X, Y at the input and I am getting at the output F is equal to X dot Y, which is simply AND gate function. Clear, girls?
Yes.
Okay.
Yes, clear.
And second one is what? Yeah, clear. Next one is the OR gate. So simply here actually they are showing here NOT gate. You just consider NOT gate as a, this gate is shown at the top. Just replace this NOT gate with that one. Then you can implement OR gate function as well. Okay, you can implement OR gate function as well. So you just go through step by step and you can basically easily understand that one. Okay, now actually I want to explain to you the type of questions which will coming to you to basically for the solution. So let's do one thing. Rather than this one, I'll try to show you the white. Just okay. Now just stop sharing from this side and share my whiteboard. Okay. All right. So see, the question is like that. I'm asking you a question, like I can give you any Boolean function, girls, and I can ask you implement that Boolean function with the help of not this NAND gate only, for example. So let's see if this is the function f, but I will explain NAND gate only. Today I was planning to just, can I, where is that? Where is that? It is really difficult to make this. it's difficult from this device. I think I'll do one thing. Whiteboard. Is this okay, girls? Are you comfortable? Should I continue lecture or stop? What do you think? Maybe if you are tired, or should I at least continue this one question with the NAND gate?
The one question is fine.
One question. Inshallah, I will try to just explain one question. So, can you see this whiteboard?
Yes.
Yes.
Okay. So, I'll show the screen here. Okay. I will take from my device. Mobile phone is not working very well. So, okay. So, question is like that, girls. We know that NAND gate and NOR gate both are universal gate. It means with the help of these two gates, I can implement any function. Okay, so here I am giving you a function and I will ask you to implement with the help of AND gate on, with the help of NAND gate only. So the function is, let's say, this is the function f is equal to a complement dot b s c d complement. This is the function given to you, and I'm asking you, if I ask you just implement with the help of basic gates, so you know that use the two AND gate and just implement that by with one more, or you can do this one. But I'm asking you to do just implement with the help of NAND gate only. What is my question? Implement with the help of NAND gate only. So I'm saying, I'm just writing implement using NAND gate only. Means you cannot use any other gate now. You will be using NAND gate only. Okay. Now, how can you solve this type of question? For that, I'll tell you first what is NOT gate symbol. This is NOT gate symbol, guys. All right. NOT gate symbol is basically is that NAND gate, not I'm saying wrong, not gate. So this is NAND gate. We have inputs, one in another input, and let the input is, this is A, another input is B. Can you tell me the function? What is the function? Output of this gate?
A dot B.
What will be the function?
All the complement.
Sorry, A dot B.
Complement all.
A dot B and whole bar, correct?
Yes.
All right. Okay, fine. Can we apply here De Morgan theorem to open this one?
Yes.
What it will be then if I apply De Morgan theorem?
The complement of A plus
Yeah.
B.
Plus
All
B.
right. Correct. Yeah, absolutely right. So this is basically applying the De Morgan law, and you know that De Morgan, if this is valid, another one is also valid because of duality theorem. Okay, if A dot B complement is valid, another one A complement plus B complement is also valid. Okay, let's see this one. A complement plus B complement. I can design a new symbol. Or what is that? What is new dry symbol mean? Basically, I can do one thing, that I can make this gate symbol A, B. The bubble, what is there, girls? Bubble will give the complement, and it's gonna be A complement. It's gonna be B complement because of the bubble. So and overall, this is next is the OR gate. So first complement, then OR gate. So what will be the function after that one? It will be A complement plus B complement. You getting this?
Yes.
So can we say both gates are implementing the same thing. Both are NAND gates.
Yes.
Okay. Okay. Now the point is why I explained to you girls, because these two representation is going to help you a lot while you are going to implement the any function with help of NAND. You know, see the first one. In the first one, this is the representation of what? Yani, whenever multiplication representation, whenever you have a multiplication term in you, will be using this kind of representation. If you have any product, any sum term in your function, you will be using this kind of representation. If you follow the rule, then you can implement any function with the help of these AND gate. Now coming to the business, how can we do this one? So removing this one and leaving this representation for your reference left side. Now I will implement the original function, which is f is equal to b plus c dot d complement. Please, everyone, you look first this one. Is product term or sum term?
Product.
Product. So which symbol I should use? Which representation of NAND gate I should use, as I just explained to you? First one or second one?
The first one.
This is first, the one. Absolutely right. So I will be drawing the first representation like that. What are the inputs? Just write A, B. Can you tell me what will be the output of this gate?
The negation of A.
No. Why negation? It will be A dot B whole complement. Am I right?
Yes.
Because this is NAND gate, na? It will be A dot B whole complement. Clear? Okay. Okay. Go for the second term, which is C dot D. So C dot D is a product term again. So I will use one more NAND gate, the first representation, and it will be simply C D here. So I will be getting here C dot D whole complement. Clear, girls?
Yes.
After the step, please focus here, every one of you. You have to check after the first implementation, you just look what is under the bar, what is under the whole bar, the output of these gates under the whole bar. Is this same which is there in the function, or something is different? You forget about the bar, top bar we will remove later, but under the bar, which is A dot B, is this same which you have to implement? We have to implement A bar dot B, right?
Yes, sir.
Yes.
As a function, or function A bar B. But here what we have? A dot B. Clear? So what I have to do, girls, here, you forget the top bar because the whole bar is gonna, compensate later on. But here what we have to check under that whole bar, we should have same function what is here. We should have under the bar same. Do we have now? No. What is missing? A complement. Am I right?
Yes.
What I will do, I will put here complement. Because of this complement, I will be having this complement here. Now it's clear. So under the bar, are you getting exactly same function which I should implement like this? A complement dot B. Are you getting? Okay, go for the second. Second, C dot D. Are you going? Is it same, or I should make a complement here?
I should make D complement.
Yes. So this is very first step, girls. Always in a first step, you have to check under the whole bar. whole bar, don't worry about the whole bar, we will replace later on. But we should have exactly same product term which is there in the given original function. All right. Now please tell me, give me the answer. Overall, this function, how we are implementing, is some term or not? Is some term. And for the sum term, which type of representation we should use of the NAND gate? First representation, second representation.
The second representation.
Second representation, because second representation is helpful for us why we are implementing some terms. So I will be putting here second representation gate. Okay, just have the C color. Okay, which is second. Again, second representation, again, not NAND gate. We are not using any other gate. This is again NAND gate. Okay, and this is coming like that, connect like that. So girls, because of the bubble, what will happen? Can you tell me when this signal will pass through this bubble, what will happen? We will be having here A complement dot B. One complement was already there, and one more because of this bubble. Are you getting point?
Clear.
Go second, another one. This will be C dot D complement. One complement was there, another one because of this bubble, as I mentioned. So do you know that double bars will cancel each other?
Yes.
No double. Okay. So what I will be getting here? Next is what? Basically, it's like a OR gate, because first it is complementing, then it is working as a OR. So what I will be getting here?
The negation of
A
A
complement
plus
B
negation of D.
So is this the same function which I want to implement?
Yes.
Yes.
Okay. Hope it is clear to you that these two representation is gonna help me here to implement the function. And see, I didn't use any other gate. I just use NAND gate, but yeah, two different representation so that we can easily implement. By the way, if you want to change the second representation by the first one representation, you can change it now. But both are implemented same NAND gate. This is not new. Both are same actually. So you can do easily this. Okay. So hope it here to you girls, and inshallah you can implement this one. So if you allow, I am giving you one question and you do yourself and tell me in between. Or if you don't want to try, it's up to you. Because I am giving you this one. Let's say this one. B, not this one. It is already covered. So let's say if I give you A plus B, yani something changing here, so that you can apply the concept I just explained to you. C, okay, no need for the bracket if I am having this one like that. CD, and let's say it is half bar and we have whole bar. This is complicated function for you, and I'm asking you guys implement this one using NAND gate only. So can you do this quickly now? Hope you remember which representation I should use. One representation for the product term, second representation for the sum term. So just look one by one. This one, which is this?
OR gate.
OR gate. No, yani second representation or first representation?
Second
Which representation I
representation.
choose here? Second representation. Yes, absolutely right. Second representation, yani this type of representation, which is not OR. What is that? Not OR representation. Yani I will be using here A, I will be using here B, then it will be giving me a complement, it will be giving B complement, and here I will be getting what? A complement plus B complement. Am I right?
Yes.
Okay, what about the second C dot D complement? Which presentation I should use? First one or second one? One. C and D complement. So what I will be getting here? Tell me.
C dot D complement.
Okay, I told you we have to make sure that whatever we have under the bar should have the same. Okay, so we got it like that. But what about the first one? We are getting A plus B plus A complement plus B complement, but here we have what? A plus B complement. So what should I do? Where should I make changes here so that I can have A B complement?
We should make a complement.
Correct this one?
A complement.
Right? Yeah. So because of complement, what I will be getting simply I will be getting A here. A plus B complement. Correct this one, girls, up to now?
Yes.
Is this clear? Now
Yes.
overall about this function, this overall function, is this product or not?
Yes. Good.
Yes.
So which representation, first or second?
First.
First. So for overall, because of product, so we are going to have a first representation which is like that. Okay. Now, so look here, we are going to have this, for example, and we are going to have this one. So now what I will be getting here at the output, can you tell me?
A complement.
Plus
A complement.
Then dot
B complement.
C dot D
D
complement
dot
whole
D
bar.
complement, whole bar complement.
Then overall bar because of the bubble at this, because of the bubble. Okay. Now,
Okay.
is this the same or some problem is there?
There's a problem.
Where?
See the D complement, there's a bar above it.
Above it. We should not have this one, correct?
Yeah.
Rest is okay? Everything okay?
Yes.
Rest is everything okay. The problem is with the bar, which should not be at the C dot D complement, correct? So I already explained to you girls how to use a NAND gate as a NOT gate. Do you know how to use a NAND gate as a NOT gate?
Yes, use the same input as
This
the,
one, this yeah, Nina, running the into single X, we will be getting X complement, correct? All right. So if we make an arrangement, some arrangement here, remove the bar of this one. So this will remove that bar in my final expression. So what I am going to do here, I'm going to insert here a NAND gate, which is going to work as a NOT gate. And because of it, this bar will remove. So what I'm going to do, look here now. I will replace, will just say remove from here something, and I will place here NOT gate as a NAND gate. So this is my NAND gate. Okay, is connected from here. Input is again from here, and combining them. Okay, and I'll be getting its output from here and connecting here. So what will happen now, girls? You will see what will happen now. X dot D complement whole bar is there. So what will be there? Can you tell me? Because it's behaving like a NOT gate. Am I right or not?
yes.
Yes.
So what I will be getting at the output, C dot D complement, one complement and one more complement because of the NAND.